So are there any questions whatsoever, or do I start a new topic? Not a new topic. Do we continue with the classes? So there's a couple of minutes to come up with questions, if any. If not, we will move on to the next part of the digital course.
Sir, I have
Yeah.
a request. Sir,
Yeah.
can you please give us some feedback on our performance in the midterm and class next? It will be helpful, sir.
Well, I will. Okay, but it will take me some time to compile the whole thing together. So by the end of this week, you will get that. Okay.
Okay, sir.
Some of
Thank
you
you.
have done rather well, but there have been a few cases which are not that great, and some cases which were not very, let's say, okay, not very kosher, if you know what I mean. Okay, request noted. So no questions whatsoever. Then we can move on to the next topic. Fine. So I'm assuming that everybody has understood everything on oscillators, which of course gives me full right to ask whatever difficult question I want to. Okay. So next, what we will do is we will move on to a kind of circuit that we want. Okay, maybe what I will do is something else. Let me just do one thing. Let's complete this part first. Okay. So maybe what I will do is instead of the recorded lecture that we have for this, let me just quickly recapitulate this part because this is going to be important. So what we have are Boolean circuits, which we want to discuss. However, there are basically two different kinds of Boolean circuits. One is called combinatorial, in which basically you combine various Boolean gates or gates which implement Boolean functions, and ultimately you want to implement a Boolean function using that. Now, those are the most common kinds of circuits that you may have seen before, but there are other more useful circuits you can make with Boolean gates which actually don't really implement Boolean functions. We will describe that later. For the time being, let's take a look at the combinatorial Boolean circuits. The simplest ones are of course and, or, and not, but this one is pretty important in itself. It's called the Xor gate. The full word stands for, the name actually stands for exclusive OR. So as you all know, in English, we use the word or in two different meanings. We sometimes say or just in the sense something could be either this or that, or perhaps both. However, exclusive or is something like if I say if you don't score 20 in tomorrow's class test, you will fail. Well, rather, let me book this statement using the or. You score 20 in tomorrow's class test or you fail. That's not true. Don't worry. You will not fail if you don't score 20 in tomorrow's class test. But if I make a statement like that, score 20 in tomorrow's class test or you fail. And let's assume that that's a proper threat. Then, of course, you either score 20 in tomorrow's class test, in which case you don't fail. That's fine. So if you say score 20 is this one and fail is this one, the statement that I have made that you either score 20 or you fail, well, if both happens, both are false. That is, you don't score 20 and you don't fail, then that statement of course is false. Okay. If you don't score 20 and you fail, then what I said was true. So that works fine. This one also works fine because you have not scored 20 and you have not failed, then the statement is false. So that's what the zero says here. You score 20 and you don't fail, that's also fine. But it would have been disastrous if the or had been in the standard A or B sense. Because then, if both were high, you would end up with a high, which of course is very, very wrong, right? If you scored 20 and you failed, that would be very unfair. So, when you say score 20 or you fail, the statement you are making is in the exclusive or sense. That is, both of this result is true. That is, or you fail, score 20 or you fail. This compound statement is true if one of the statements is true or the other one is true, but it's false if both of them are true or both of them are false. That's why exclusive is the adjective that we use here. Inclusive or, which is the ordinary or, is true when any one of the inputs is true. Exclusive or is true only when exactly one of the two inputs is true and the other one is false. And of course, if you want to write this in terms of standard Boolean and or not, is straightforward. This one is A bar. That is, this one is true when A bar is high and B is high. So this line would be 1 if you had A bar B. A bar B, of course, would be just 0, 1, 0, 0. High only when A is false, B is true. On the other hand, this one is high when A is true, B is false. That would have had a truth table like this 0, 0, 1, 0. And when you OR these two statements together, and this, of course, is the standard OR, the inclusive OR, then you get a high when any one of these two are high. So you get 0, 1, 1, 0. That's what A XOR B is. The XOR actually happens to be a very important gate, despite the fact that it's not one of the standard gates. It's one very important gate for a very for a very good reason. And in fact, it happens to be a gate which is used very, very often in cryptography for this reason. Can anybody tell me what this is? If I did explore exclusive or twice of A with B, what would the result be? Yes? Any idea about this one? Am I still connected or not?
A.
A. How do you figure that out?
Just do A or B and write down and solve the math.
In other words, what do you really do? You write down the transcript table, or do you write down AB bar plus A bar B,
Yeah.
then do it again?
Oh,
Hmm? So when you say do the math, what do you mean by do the math?
I
And of course,
mean,
write down.
yeah, write down and just A bar B. I say write down A B bar and A bar
Oh,
B and multiply.
okay. So there are several ways, of course, of doing it. What you could, of course, do is something like this. You already have the truth table. What you have done is fine. All I'm saying is there are many ways of doing it. One of them is because you can see that you have A, B and A XOR B's truth table right here, we can add one more column to this and try to work out what A XOR B's XOR B is going to be by writing down the truth table. So for this, you have to focus on these two columns, of course. This is B and this is A XOR B. You want to XOR the two together. And the basic idea about XOR is you get a high when the two inputs are different and low when they're the same. So you get low here, where both of these columns are the same input. Here again, same input. Here, opposite input, opposite input. Of course, now you can compare this column directly to this first one and see that A XOR B XORed with B is actually the same as A. That's one way of doing it. The other way of doing it would be to simply use this. I think that's what you were saying. If you start with A XOR B is AB bar plus A bar B, then what you can do, okay, I need some space here. So let me just create a new page. So this is A XOR B, which is AB bar plus A bar B. Now if you did it twice like this, it's really A XOR B times B bar plus A XOR B's complement times B. And you can carry out the whole calculation. This is AB bar plus A bar B, B bar. On the other hand, there is a complement of this thing, AB bar plus A bar B. You can work it out in full by using De Morgan's theorem, or you could simply realize that the truth table we had, its complement would simply look like 1001. That would be AB plus A bar B bar. Just write this down. AB plus now use Boolean algebra. AB bar, B bar is just AB bar, right? Because B bar is B bar. On the other hand, A bar B, B bar. What is that? What is B bar?
Zero.
Yeah, zero or false. Because B bar simply says B and not B, and that's simply not possible. You cannot have B and not B high at the same time. So this is A0, A bar 0. A bar 0 is, of course, 0. So 0 meaning false, of course. Then ABB is just AB. A bar B is 0 for the same reason. And odding with 0, A or 0 is always A. So you can ignore these zeros. You're just left with A, B bar plus B, or B bar or B. And B bar or B is always true because B has to be true. If B is not true, then B bar has to be true. One of the two inputs is always true. So what you have is A times 1, A and 1, that's A. So that's a Boolean algebra way of working it out. Slightly more complicated and lengthy than just looking at the truth table. In this case, the truth table was so simple that you could just take a look at it and work out the answer. But usually, things are not always that simple. So A and 1 is A. Ultimately, you land up with this result. Now, there are other ways of doing it. But the best way perhaps would be this. If you look at this particular truth table once again, 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1, the last one, is 0. Now, let's just focus on what's happening to A as opposed to this. That is, if you think of B as something which controls what happens to A here, notice what happens when B is 0. B is 0 is for these two lines, right? If B is 0, the output is exactly what? How do you compare the output with with A in that case, if B is 0? What is it? Then either look at the truth table or simply look at AB bar plus A bar B and try to figure out what happens when B is low from here. Get the same result anyway. So when B is low, what does it tell you about A bar B? Come on, that's a trivial question actually.
It's A.
You mean the whole thing is A, right?
Yes.
Yeah, I can easily see that. You have 0, either from the truth table, you can see 0, 1 for A, gives you exactly 0, 1 as A XOR B. Or you can just use this statement that if B is low, then this term goes away. And then B bar is 1, so A B bar is just A. So this is it. But if B is 1, then A XOR B is what? Again, either the truth table or this one. Just look at these lines, these two lines, and compare A with A XOR B in this case. Because B is 1 in these cases. So what's the connection?
A bar.
A bar. So what one way of thinking about the XOR operation is like a controlled inversion. That is, A is inverted if B is high, and A is not inverted if B is low. But this is actually very, very important in applications. This may be a trivial thing which comes directly from either the truth table or from this expression. That's, in both ways, it's trivial to really work out, but it's actually very, very useful. The fact that XOR actually does controlled inversion. Okay. Now, using this idea of controlled inversion, let's think about what this really tells you. If B is low, then A XOR B does not invert. A XOR B just returns A. So A XOR B here returns A, and B is still low. After all, this is only one B. So A XOR this A XOR with B gives you A. So you get A back if B is low. What happens if B is high? Well, the first A XOR B inverts A then, and the next XOR with B inverts it back. So if you invert twice, you get back the original thing, right? So either way, irrespective of whether B is low or high, if B is low, A XOR B just returns A, so you get A back both times. So you end up with A. If B is high, A XOR B inverts the second XOR inverts again, so you're back where you were. Okay? So the controlled inverter view of A XOR B makes it very easy to figure out that you are either inverting twice if B is high, or not inverting at all if B is low. Either way, you're going to get back A. Okay? Now, this is a pretty straightforward and simple result, but we are spending quite a lot of time on this because quite a lot of important results actually hinge on this behavior of XOR. Okay, and since although this is really not part of your course, I would want to give you one kind of insight onto an entirely different subject where this double inversion or no inversion at all, this behavior XOR B, actually plays a very important role, and it's a pretty interesting subject. And the subject actually has to do with secret codes. So this is just primarily for interest. This is not really part of a physics course anyway. But let me just ask all of you, is there any code which cannot be broken at all? Or can every code be broken? What's your idea? I'm just asking for your opinion. Somebody has created a secret message using a code. Given enough time and enough information, can this code be broken? Or can all codes be broken? Or do you have something which is definitely unbreakable, provably unbreakable? Yes?
I guess everything can be broken.
Every code can be broken.
Yes.
Well, of course, if you have a very small piece of a coded message, then it definitely cannot be broken. That's absurd. But what do you say that you mean that given enough information, given enough pieces of messages and so on, you should be able to break the code, right?
Yes.
Well, let me prove to you that there is a code which simply can never be broken. And it's a very straightforward code. This code is basically this completely unbreakable code or probably unbreakable code is something which goes under the name of Varnam cipher after the fellow who talked about it, but has a simpler name. It's called one-time pads. The basic idea is this: every coded message can be ultimately converted into numbers, right? Every message that you have, you can find some kind of encoding which will change it into a bunch of numbers, right? If nothing else, you can say A is 1, B is 2, C is 3, and go with that. Okay? So ultimately, everything can be made into numbers. That's our first point. And then, since every number can be written down in binary, every number can be written down in binary numbers. I'm not really talking about the original Varnam cipher. I'm talking about the version which is going to be easiest for us to talk about. So suppose our original message is this. Some strings of ones and zeros, which is supposed to, which if somebody read it and passed it to an appropriate machine, perhaps, it would give you exactly the right message, whatever the message was. As far as we are concerned, we are not even bothered about what the message was in English or Bengali or Hindi or whatever language. This is our message, this strings of zeros and ones. Okay. Now suppose there's a random key. Somebody has a key which is again a strings of zeros and ones and completely random. Say, let me just write the key in a different color. Say 00110100100001. Let's say. So this is a completely random bunch of zeros and ones. The message, of course, is not random. It is built out of a particularly precise method, starting from whatever plain language message you had. Okay. So the cipher or the coded message that will be created like this. What you do is you take corresponding bits in the message and the key and XOR them. So 0, 0, same two inputs, XOR is 0. Here, 1. Here, 1. Here, 1. Because these are different, right? 1, 0 is 1. 1, 1 again, 0. 0. 0. 1, 1, 0. 1, 0 is 1. 1, 1, 0 is 1. 0, 0 is 0. 0, 1 is 1. 0, 0 is 0. So this is your cipher. Okay? Exactly as long as the original message. Of course, I'm assuming you have a long enough key for that. And the key is never repeated. It's just a thing of random zeros and ones. So this is your cipher message. I'm claiming that this is provably unbreakable in the sense that if you just have the cipher message in your hands, cipher message, don't have the key, then it's impossible to recreate the message. Can you see why? When I say it's impossible, I mean I can prove that it's impossible by a very simple argument.
But there is a binary operation between message and key.
Yeah, there is. But what makes it an unbreakable thing?
So without key, how do we know the result of that binary operation?
No, that would be the case for every kind of coding, right? How would we know is not a proof. When I say proof, I mean a precise mathematical proof. Okay, I will give you that to you in a non-mathematical language. But the point is simply this. Any given bit here, say this is 0. Why is this 0? Because the key matched the message. But the key is completely random, right? So the key could have been either 0 or 1 here with equal probability. It just happens to be 0. It could also have been 1 because the key is completely random. And the probability of it being 1 is the same as the probability of it being 0. So unless you know the key, you have no clue about what this particular bit is. It could be 0, it could be 1 with equal probability. It would mean that the cipher would end up being either 0 or 1 with probability, or if you look at it the other way around, if you look at the cipher and it's 0, can you tell me what the message was? The answer is no, because if you don't know the key, the message could have been 0. Say, suppose the key was 0, then the message had to be 0. Only that will give you 0 as cipher. But if the key had been 1, the message must have been 1, but only then you will get 0. My point is, if you do not know whether the key is 0 or 1 at a particular bit, but just know that it's a random key, so it will be 0 or 1 with equal probability, then from the cipher result, you can only recover the message. Well, you cannot recover the message. It's not you can only recover the message. You can do nothing about whether the bit in that particular message was 0 or 1. In fact, it's equally likely to be 0 or 1. And frankly, what this means is if you are just given the cipher message, only thing you can say about the message is how long the message is, how many bits it has. Other than that, every message which has the same number of bits would be equally likely. Because one or the other random key would have given you that, and there is no way you can actually claim that this random key is better than that random key. Is that clear? That is, if this is n bits long, the message, then there are 2 to the power n possible messages. And out of the 2 to the n possible messages, each one is just as likely as the other one. But now, the real question is, how do you decode? Because a key, I could just take a message and completely garble it up and call that a cipher, but that would be useless, right? Because then it's true that nobody can recover the message, but the purpose of a coded message is not that nobody can recover it. The purpose of a coded message is nobody who is not allowed to, or whom we have not decided to share it with, can recover it. If nobody can recover the message, then the message is lost. Then it's useless. But how do you decode the message? Suppose I have given, this is the message, I have not sent it to anybody. This key is with some other person, somebody else has the key, and that person has received the cipher. How would that person decode it?
Key XOR cipher.
Exactly, because you have XORed message with the key to get the cipher. You have taken every bit, and you have taken the message, taken the key, and you have produced the cipher out of it. Okay? Right? By XORing message with the key. Now, XOR the cipher with the key, you are essentially doing message, XOR key, XOR key. That gives you back the message. So see, 0, 0. Same tells you 0. 0, 1, 1. 1, 1, 0. 1, 1, 0. 0, 1, 1. 1, 0, 1. Notice that I'm recovering the message completely. 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 0 again, 0 here, 0 here. Notice that the message has come back completely. This is exactly the same as the original message. But in order to recover the message from the cipher, you have to actually use the key. So the person who is reading this has to have the key with him or her. Without the key, all messages are equally likely. That is, if you are just being given the cipher, somebody must have, may have tapped into a telephone line or something, or hacked into your computer, read the cipher message. As far as that person is concerned, he has absolutely no clue about what the actual message is. because every message would have been equally likely to him or her. What is not equally likely is if you have the key. If you have the key, then you can immediately recover the message. Okay. And the basic thing here is the XOR gate. Do XOR twice, and this property of the XOR. Doing XOR twice gives you back everything. So XOR it once, then the message and key get entangled together in a way. The key being random, the cipher becomes completely random. In this sense, that if you don't have the key, it's completely random. But this A XOR B being A tells you that you just have to XOR once again and you have got back your original message. Now, of course, the part would take me way too far ahead of this course, but that's something I can do in a course next year. What is the one problem with one-time pads? Can anybody tell me that? This one-time pad happened to be a very, very important method of sending codes. It still is. But what is the one problem that one-time pads have? Okay, they are called one-time pads for the simple reason that these keys, you have, in the traditional old school way, you had a pad with each sheet having these random keys, one random key each, and you were supposed to use one random key only once for a message. Then you discard a page from the pad, use the next page. Which is why the random key is never repeated. So you don't get to see any patterns people would actually rely on to break. Can anybody see what is the problem with one-time pads?
You said that the key should be random, but we know that nothing can be completely random. Not as of yet.
True, but it doesn't really matter because you are not even sending infinitely long messages, right? Given the size of the message, you can always create things which, in fact, there are things which are definitely completely random.
The memory requirement is also twice.
Mm-hmm.
The
Why?
memory requirement is also because we have to, like, if I am sending the message, like, I have to send the key also.
Wait a minute, that's where your real problem is. How would you send the key? The same thing as the message? If somebody hacks in or taps you and listens to your message, they can equally easily learn the key, right? You would never send the message and a key together. Then you might just as well say key and the cipher together. You never send the message, by the way. The message is with you. You send the cipher coded message. But you send the coded message and the key, then it's not a memory requirement, it's a transmission requirement that you're worried about. Memory is what you keep with you. Transmission or network requirement is how much you send over the network to somebody else, whatever the network may be. Could be a telephone call, could be a newspaper ad, whatever. But the key and the cipher, you send them together. If you did that, then you might just as well print the message. The point in sending that. Okay, so the fact that you have to do it twice, that is, you have to send the key and the cipher, is not the issue. You will never do that. But then you're on the right track in a way. How does one get the key? That the point is the person who is supposed to receive the message, the actual legitimate receiver, that person should have access to the key, right? So one-time pads, one-time was precisely that. Spies used to carry one-time pads which are created specially for them. Physical pads. You created two copies, one for the sender, one for the receiver, and they used page number 1 for the first message, page number 2 for the second message, and so on. The problem is physical one-time pads are. How do you get them to people? They must get together with at least one person at one time, right? Otherwise, how would they get physical access? Or somebody has to send the pads. And all these steps are prone to hacking. If two people get together, then somebody else might be able to spot them that they're together. They may be able to steal their one-time pads. Even better, make copies of one-time pads so that The two people don't even know that somebody else is reading their messages. And okay, these are not fancy just stories, because this has been done in wartime, even in peacetime. Okay? In fact, the reason why the World War won by the Allied powers and not by the Axis was more due to the fact that the codes of one team was broken more often by the other team, rather than essentially by any of these military prowess, because the military prowess was very balanced. The reason why Hitler lost was basically, you must have heard of the Enigma machine, at least you should have. The Enigma code was broken by one of the greatest computer scientists of all time, Alan Turing and his team. So, apart from that, even one-time pads, which are much more low-key, much less technically important, they were more effective, and they were broken simply by people who risked their lives to get the pads from, at least get at the pads, get at enemy pads. The real problem is key distribution. That is how to get the key from the sender to the receiver, or from a single central position to both sender and receiver, without compromising it, without somebody else getting to know it. And that is where one of the most important modern innovations come in. Today we have something called quantum cryptography, which you may or may not have heard of. At least next semester there will be next year there is a course on quantum information theory, which you may want to take, and part of that is quantum cryptography, where there's a wonderful way in which you use the fundamentals of quantum mechanics, things that you're learning right now, and put it to practical use. That is, use it to actually transmit coded messages, not really coded messages, use it to transmit keys from one place to another. And quantum cryptography, unlike quantum computation, which is still in its infancy as far as practical applications are concerned, quantum cryptography is actually quite practically applied nowadays. It's used actually in real businesses or government communications. It's a practical application of the fundamentals of quantum mechanics, which you are sort of learning right now. Things like the superposition principle and collapse of the wave packet and stuff like that. Anyway, that will take us too far, I feel, from our Boolean Algebra course. So that's for your next year. But let me just point out that at the heart of all this is the simple behavior of the XOR gate, that if you XOR twice, you get back what you started with. Now, let me just quickly go back to our XOR gate, because I've already spent way too much time in this. Okay. So this is a symbol for the XOR gate. XOR is so important that it deserves a symbol of its own, and in many circuits you don't really write down the XOR gate using A bar B combinations and or NOT gates. You actually just have a single symbol for the XOR, which is the OR with an additional bend bar in front. So without this bend bar, this one, it would have been A or B. With this, the symbol stands for A XOR B. And this circuit, of course, is trivial. It just says AB bar. You are producing AB bar here. You're sending A to a NOT gate to produce A bar, and then sending B in. So you get A bar B, and you're ORing them. So this is how you would produce the A XOR B or XOR gate, by using AND or NOT gates. That's on the right. But very often, this is not produced this way, because this is so important that you can buy chips with XOR gates built in. So basically integrated circuits which actually produce the XOR operation directly. Okay. So now, let me show you a very, very trivial and simple application of the XOR gate. Here you have 8 XOR gates, and these D0, D1, D2, D3, D4, D5, D6, D7 are the inputs to the XOR gate. Of course, to the XOR gates, but each XOR gate has 2 inputs. And the second input is joined to this line called inf. And this is the output line. So it should be pretty easy to guess what this does. What does this do? It depends, of course, on what this inv is. Inv, of course, is a Boolean variable, can be either low or high. So if inv is low, how is the output related to the input? By the way, this is a byte of input, right? Because you have 8 inputs, 8 bits. So that's 1 byte which is going into this, 1 byte which is coming out. And the reason why I'm using the bit byte language is that this is really a part of computer circuitry. This is used in a real digital computer. And so it does a very simple thing, but it's a very important thing now, nonetheless. So what does it do? If inv is low, how is the output byte related to the input byte?
Both are same.
Both are same. If inv is high,
then output is low always.
no, it's not necessarily low.
It's the complement of the input.
Yeah, it's exactly the complement of the input, bitwise complement. If inv is high, y0 is g0 bar, y1 is g1 bar, y2 is g2 bar, and so on. So you have an 8-bit number. It's basically a Boolean sequence of 8 bits. You can also think of that as a binary number made out of zeros and ones. And y is either the same or its complement. By the way, it's actually called its ones complement. Now, I'm not sure whether this is taught to you in class 12. It wasn't when we were students, but many syllabi actually teaches this to you. And I'm pretty sure you must have heard ones complement or two's complement in your computer classes. Am I right about that?
Sir, yes, sir. It was a part of graduation course in 3rd semester.
In graduation course. What is graduation course? Sorry.
Sir, I PhD. So in our university in 3rd semester,
Okay,
there was
your university
electronics.
was there in the 3rd semester. Okay, it would be.
Yes, sir.
I guess. So what about the BSMS students here? Have you heard of one's complement or two's complement?
So people who had computer science in school should have heard of it. Otherwise,
Yeah, but you had two computer courses so far, right?
Yes, but I don't
In
think
high
there
school.
was one's complement or two's complement specifically done in those courses.
Okay, so we are going to talk about one's complement, two's complement, what they are soon. But right now you understand what is being said here, right? If you have a series of 8 bits, let's say 0, 1, 1, 0, 1, 1, 0, 0. If this is the input, that is 0, 1, so 0, 0, 1, 1, 0, 1, 1, 0, and so on. These 8 bits were given to D0, D1, D2, and right now. By the way, you read it from the left to right. So you are going to write this is D7, this is D6, and so on. If the inv were high, the output would have been 1, 0, 0, 1, 0, 0, 1, 1. This number is called the ones complement, or to be more precise, the 8-bit ones complement of this number. Just all the zeros have changed to 1, all the ones have changed to 0. We are going to come to why this is very important soon. That we need to before we have to talk about the next real application of this circuit. But before we go there, let me just come to another very simple circuit. Again, something which many of you already perhaps know about. It's called a half adder. And what it does is simply it adds 2 bits. Okay. Adds in the sense of addition, not in A plus B as A or B, but A plus B really as A added to B. Okay. Now, one point is this. A half adder has to have 2 inputs and 2 outputs. 2 inputs because it's adding 2 bits. You give the 2 bits to A and B, the inputs here. But you also need 2 outputs. Now, why do you need 2 outputs? The answer is simple. If you add a 0 to a 0, what do you get? Think of these as actually binary numbers and not Boolean variables. So this is real addition. So what is 0 plus 0? It's obviously 0. What's 0 plus 1? It's again obviously 1. What's 1 plus 0? That's again obviously 1. What's 1 plus 1? How much is 1 plus 1? Come on. Nursery.
1 0.
Well, 1 plus 1 is 2, right? But you cannot write down 2 as a single bit. Because in binary, there are only two values possible, 0 and 1. So the moment you have 2, you have to use 1 0. So that is, you get 0 as a sum and 1 as a carry. I hope everybody remembers this from their nursery classes. Right? Now, of course, you did not have a carry in the other cases, but then you would have said the other cases had a carry of 0. You cannot suddenly switch from one output to 2 outputs when the input changes. You always have to have 2 outputs, one for the carry, one for the sum. And this is what is going on. If A and B is 0, okay, the sum, the actual addition, this is really the actual addition. 0 and 0 together gives you 0. I've written this with 2 bits as 0, 0, then 0, 1, 0, 1, and finally 1, 0. That's the number 2. Okay. So if you look at the C and D here, D is actually the sum here, and C is the carry. Carry is high only when you have 1 and 1, and carry is low otherwise. And the sum, on the other hand, is simply 0, 1, 1, and 0. So that's what you have. So this is what the half adder circuit's output is. You have 2 inputs, A and B, 2 outputs, which produce 0001 or 0110. And it's very easy to write down the Boolean expressions for this. If you forget about the fact that these are actually adding numbers and just think of these as Boolean expressions, C is high only when both inputs are high, that obviously is AB. And D, on the other hand, is high when the 2 inputs are different. So when they are the same, that's of course our XOR B. So basically, this is what the half adder circuit is. You take A and B, send them to an XOR gate, you get the sum, which is our bit D, and you send them to the AND gate, you get carry. That's it. So that's the carry and the sum. Okay? Question. Why do we call this a half adder? And of course, those of you in the PhD would already know the answer. But I'm asking the others, can you guess? Why would this thing does a perfectly good job of addition, right? It takes 2 inputs, adds them together. Why would anybody want to call this half adder? Of course, that's because there is something called a full adder. Why is this only half an addition? Strictly speaking, it's not really half an addition, it's just, but it's not a complete addition. Let me just ask you this. Suppose you were to add 2 numbers. Let's talk about decimal numbers for the time being. That's easier for us to sort of 293 with 325, let's say. When you add them together, you're adding 2 decimal numbers together. That means you're adding digits, right? You're adding the ones digits first, then the twos, then the tens digits, then the hundreds digits, and so on. Right? 3 and 5 added together gives you 8. But the question is, when you add 2 decimal numbers together, do you always add 2 digits? That's the question. Is that true? This is again class, well, KG or not KG perhaps. Maybe for class 1. I don't know. I don't remember that far back. But when you add 2 decimal numbers together, multi-digit decimal numbers together, do you always add 2 bits? Yes or no? Yes, no, maybe. So when you are adding these 2 bits, two digits, Are you adding 2 digits? Yes or no? Yes? Is everybody asleep? When you add these, adding 2 or not?
Yes, sir, we are adding.
Yeah, but when you're adding these two, are you going to add 2 bits, 2 digits?
No, sir, we will also add the carry.
Yeah. The moment you have 9 and 2, you have 1 as a sum, 1 as a carry. So in order to add 2 numbers, you cannot add 2 digits all the time. In binary, that works in Boolean as well. And in Boolean, you get a carry much more often than you get in decimal addition. The important point is, since you're going to add any 2 set of numbers, your circuit has to be able to add whatever numbers are given to you. And there will be carries. So typically, if you have carries, you're actually not going to add 2 bits or 2 digits as in this case, but 3. So that's why this is called a half adder. It adds 2 bits, but it cannot really add 2 numbers, or you cannot use them to add 2 numbers. You have to have a way of adding 3. So a full adder, and a block is simply this: an, bn, cn minus 1. These are the 3 inputs. An and bn are the 2 input bits from the numbers to be added. Addends. So these are bits from the addends. Cn minus 1 is a carry in the previous step. That's why it's written n minus 1. So it comes from one step earlier. So when you're adding A3 and B3, the third 3th bit is A3, B3, by the way, are not the third bits. They're actually the 4th. If you count from the right, they're the 4th, right? Because A0, B0 are the first. So 0th, 1th, 2th, 3th. That sounds bad English, but that's perhaps best to use. So when you add the 3th bits, A3 and B3, you have to add to them together the carry from the 2th bits, so C2. A3, B3, C2 have to be added together. And when you add them together, you get a 2-bit output, the sum at the nth level and the carry in the nth level. And how do you actually add big numbers by this? This is for a single bit addition, right? 1 bit, another 1 bit. But if you have 2 4-bit numbers, for example, how do you add them? So you have A0, A1, A2, A3, that's 1 4-bit number. By the way, 4 bits are, in computer language, they're called nibble, half a byte. Not very important, but it's useful to know the term. B0, B1, B2, B3. So you're adding these two 4-bit numbers together. You're going to send A0, say A0, B0 and, okay, C minus 1. There is no carry at this level because this is the very first one that you're using here. You could either use a half adder here, or you could use a full adder. Just because you have full adders, maybe full adders are in a chip. In fact, a chip might come with several full adders built in together. So it's best not to go really try to get a half adder from somewhere else. You just use a full adder and keep the C minus 1 input grounded. That is, C minus 1 is 0. So A0, B0, there is no carry. That's all you're saying at the very first or 0th bit. So A0, B0 gives you C0 and S0. S0 is your output. C0 gets fed to the next full adder. You get A1, B1, C1 to give you C1, S1, and so on. Of course, I've just shown you a nibble adder, 2 4-bit adders, but I could just put 8 such full adders together and get a byte adder, or more of them together to get ways of adding bigger Boolean numbers. And these are actually used in computers exactly this way. Okay. And the truth table? Well, I will not spend a lot of time describing the truth table for you. You can actually figure it out yourselves. 3 bits, so there are zeros. So these are the 0, 1, 2, 3, 4, 5, 6, 7. These are the decimal numbers corresponding to that. You have these binary equivalents or 0, 0, 0, 0, 0, 1, and so on. And for each of them, you can find out what the sum and the carry is. Right? 3 zeros add to 0, sum 0, carry 0. 3, 1, 2 zeros and a 1, 2, 1, 0. 1 sum, carry 0. Here, 1, 0, 1 gives you 0, 1, and so on. Now, I can use Karnaugh maps, which we talked about in the last video, or you could use any other technique to figure out what Sn and Cn are. In fact, Cn, by the way, is the same as the majority voting that we talked about there, because carry is high when either 2 of the bits are 1 or all 3 are 1. So if majority of the input bits, 2 or more out of the 3 is 1, you will get a carry. That's easy to see, because if 2 or more are 1, you're going to get either 2 or 3. In both cases, you get a carry. So Cn is a familiar function which can be simplified either using Karnaugh maps or using a Boolean technique or whatever. It works out to be this. Sn, on the other hand, this sum is actually not very simple, because if anybody has seen the Karnaugh map video, you would know that to simplify, what you need are large blocks of ones together. Unfortunately, here all the ones are sort of separated. So you have 4 terms here. So 4 terms, each of which are only singlets. So they are big expressions Boolean wise. So to implement this circuit directly, the full adder circuit using AND or NOT gates, or using NAND gates only, things which we have described in some detail in the last 2 lectures, would actually take a lot of effort. However, the full adder circuit can actually be implemented with a lot less amount of circuitry. Of course, circuitry means cost, right? And full adders are very, very important in digital computers. In fact, most of the work is done by full adder chips, full adder gates. So if you increase the cost of that, if you can somehow decrease the cost of that, that's going to bring down the cost of a computer a lot. So the question is there a clever way to implement Sn here, this complicated looking OR of 4 inputs and so on, with less circuitry? Even 1 chip less would actually cut down the cost of a computer by a huge amount. So that's actually very, very, and also make it faster. Less chips, if each chip has a propagation delay time. Signals take time to propagate through them. Very, very tiny time by our human standards. But if they're used over and over again, that makes for a huge, huge difference. So there, what we need to see is something like this. We need to be clever. And this clever part is one which I'm not sure that even those of you who have studied full adders before, say in your previous graduation courses, recognize or have learned about this. To understand this, what we need to do is take a look at Cn bar. Cn bar, of course, has a Karnaugh map which is exactly the same, except that all the ones are zeros and all the zeros are ones. So basically, Cn bar would have this kind of simplification. So those of you who have not seen the Karnaugh map video would not understand what I'm talking about, but you should be able to figure it out yourselves after seeing the video. And Cn bar can be simplified to this. So just like Cn is An Bn plus An Cn minus 1 plus Bn Cn minus 1, Cn bar actually happens to be An bar Bn bar plus Bn bar Cn bar minus 1 plus An bar Cn bar minus 1. But that also is very easy to understand just from the basic idea. Remember, we said that the carry essentially is the majority vote, right? Because if 2 or more are ones, then the carry will be high. But when is the carry low? By exactly the same logic, carry is low when 2 or more are low. So exactly from that, you can, even without any kernel maps or any Boolean algebra, you can figure out Cn bar has to be An bar Bn bar plus Bn bar Cn bar minus 1 plus An bar Cn bar minus 1. It's the majority of nodes actually which makes Cn low. But now, the sum of the 3 input bits, the OR, not the sum actually. If you take An or Bn or Cn minus 1 and with Cn bar, well, what is that? It's An with this. But what is An with this? Can anybody tell me that? Plus Bn with this plus Cn minus 1 with this, of course. But what is An with this? An and this. Yes?
Sir, it will be An, Bn bar, Cn minus 1 bar.
Okay, that's correct. But the point is you'll get 3 terms, right? You'll get An bar, Bn bar, which is 0, because An bar is 0. An bar, Cn bar minus 1, that's also 0 or other low. And the only term which survives is this term, An, Bn, C bar, n minus 1. Very similarly, you can check if you take Bn and Cn bar, this term goes away, this term goes away, you are only left with this. And if you take Cn minus 1 with Cn bar, then these two terms go left with An bar, Bn bar, Cn minus 1. Just exactly the expression that is written there. Now, if you take a look at what Sn was essentially these 3 terms odd with one more term, An, Bn, Cn minus 1. So Sn really works out to be this. N plus Bn plus Cn minus 1 odd with Cn bar, that gives you 3 of the terms odd with A, Bn, Cn minus 1. So that's the Sn. Why is this better than before? Because once you've calculated the nth carry, which is just the majority voting box output, can complement that, or it with A and Cn and all 3 together, and that makes a much simpler circuit than all of the rest. So basically, this is how the full adder circuit really is made. Not made with a complete implementation of those Sn and Cn separately. What you really do is, well, take a look at what this does. The last line here, this part, well, you take A, B, Cn minus 1, the 3 input bits, 2 of them actually coming from the binary numbers, 1 coming from the carry. You add them pairwise to produce the 3 pieces and send them through a NOR gate. Why do you send them to a NOR gate? Because that produces Cn bar. And then you take the output and directly feed it to 4 3 input AND gates. One with Cn minus 1, one with Bn, one with An. And of course, the fourth one doesn't get Cn bar at all. It takes An, Bn, Cn minus 1, produces this. And this simply gives you Sn. Okay, so this circuit gives you Cn bar and Sn directly. Of course, you want Cn, you can just put in a additional NOT gate after that. That's all you really need. So this is how you create a full adder more economically than by actually going by the Boolean circuits. By using the full adder as 2 outputs, you use one output to produce the other one, which makes it easier for the circuitry. Okay, just to realize, if you want to realize exactly how efficient this is, what you should do is also implement Sn and Cn by using AND or NOT gates directly without taking Cn back, without taking Cn bar and feeding it back. If you do that, you would realize exactly how much more efficient this really is. So this is the way in which a full adder is really built in a digital computer. not implementing the original Boolean expressions, not this one, because this would take too many gates and would be too slow. And when I say too slow, I mean at a human level, you cannot make out the fact that this is slow at all, but you can actually make out it's pretty slow in the long situation. Okay, finally, not finally, but at least here, this is the circuit. Okay, before we go on to the circuit, actually, I need to explain to you what one's complement and two's complement are. And so to those who have already heard this before, well, you will get bored, but you have to listen to it anyway. And those who haven't, well, you should have learned this before in some class somewhere, I guess. Anyway, if you haven't, let's look at this. The basic idea is simple. You have to implement numbers in actual numbers in binary using zeros and ones, right? So maybe this is your number. So how much is this number in decimal? Well, this is 1. This would have been 2, but it's not there. This would have been 4. This is 8, 16, 32, 64. Okay. And this would have been 120. It's not there. So basically 64 plus 8 plus 1, that's 73. Okay, that's fine. So this is how you represent numbers in a computer. But how do you represent negative numbers? When you write down minus 73 on a piece of paper, you have an advantage. In addition to the digits 3 and 7, which you are using to write down the number, you also have a minus sign. So you can just put a minus sign in front and everybody knows it's negative 73. How do you write down minus 73 on a computer? First, how does one write down minus 73 in Boolean? In binary.
One add. One add.
Wait a minute. Minus 73 in binary in a piece of paper. How would you write it down? Not on a computer, but if you wanted to write down minus 73 in a computer, on a piece of paper in binary. Binary is just any other number system. You could use it just as well as decimal. How would you write that? Simple. You put a minus sign in front. Why not? Who is preventing you from using minus signs? In fact, you would perhaps not even write the leading zero in both the positive and the negative number. You would just write minus 100, 1001. That's minus 73 in binary. No problem with that. The problem comes when you want to represent this on a computer. In a computer, you don't have any minus signs because you only have zeros and ones. Everything you do has to be done with zeros and ones. So first of all, how do you indicate whether a number is negative at all or not? And the answer to that is what you were trying to say, perhaps. The way in which you indicate negative numbers on a computer, at least this is one way, the most common way, not necessarily the only way. But there are computer systems where the hardware is different and they indicate negative numbers differently. But nowadays we have a more or less worldwide standard. And according to the worldwide standard, what you do is you take these 8 bits, which you want to write the numbers in. By the way, technically this is called the LSB. This is called the MSB. These are simply shorts for least significant bit. And this one, of course, is most significant bit. Why? Because this one, if you put a 1 here, it only counts for 1. If you put a 1 here, it actually counts for 2. This one counts for 4. That's the positional number system. That's the way we write numbers. You use the same thing over and over again in different places and they mean different things. So 1771, the 1 here means just 1, the 1 here means 1000. You all know this. This is straightforward. But the 1 here would be least significant. The 1 here would be much more significant than that because it contributes a lot more. Now, what people do if you are using 8-bit numbers, of course, modern computers don't really use 8-bit numbers. They use 32-bit numbers or 64-bit numbers. They would simply be way too long to write down. So I'm just pretending that they use 8-bit numbers. So if you use an 8-bit number system, the most significant bit, the one to the left of it all, this is usually, in most systems, is a sign bit. That means positive bit is 0. The number that you're talking about is positive if it is 0 and negative if it's 1. Okay? So basically, that is precisely why you have to keep a precise count of how many bits you are using to represent a number. Because again, in the computer memory, you don't have, say, boxes like 8 bits, then 8 bits, then 8 bits. They are all one after the other, right? So they are not in separate boxes. So you have to know where one number begins and one number ends. So you have to have a precise count of how many bits you use. I'm pretending that computers use 8 bits, actually use 64 or 32, but let's just stick to 8 bits now. So if you're using 8-bit blocks, then the leftmost bit is a sign bit. If it's positive, then the number is positive. If it's then it's negative. Okay. Now, question: with 8 bits, how many numbers can you write down? Yes, that should be easy. 8
2 to
bits
the power
which
8.
can take value 0 to 1. So, how much?
2 to the power 8.
To the 8. That's, of course, in decimal or our standard way of talking about things is 256 numbers, right? Which is, of course, rather low. That is why you have to go to 32 bits or 64 bits in modern computers. With 8 bits, you have only 256 different numbers. That's it. Now, depending on which system you use, when you now talk about, okay, if you're talking about all these 8 bits being unsigned integers, that is, can only be positive numbers or 0, then what is the smallest number that you could represent? So there are several different Boolean number systems. One of them is the unsigned integer convention. These 8 bits just stand for whatever numbers you have. So what is the smallest number? Smallest numbers are 8 zeros, right? What is the largest? Largest
255.
is 8 ones, which you can, of course, figure out is 255 by adding, but you can also figure out it's 255 simply from the fact that there are 256 numbers. If you start from 0, where would you end up when you have 256? Because you are starting from 0, it's actually 255 where you end up and not 256. So 256, 5 is the largest number, 8 ones. This is when you use unsigned integers. They are very useful sometimes, but now comes the next convention. You use signed integer. Signed integer simply means the most significant bit, that's a signed bit, that's what I've been talking about. If it's 0, the number is positive. If it's 1, the number is negative. The rest of the bits, the 7 bits, carry the number. So what is the largest possible number now? And what is the smallest? So what will the largest possible number be? First of all, it had better be a positive number, so the sign bit should be 0. And the other number should be as big as possible, right? 1, 2, 3, 4, 5, 6, 7. So this is the largest positive number. How much is it? By the way, 2 to the power 7 is 128. So what is this number?
127.
Well, there are several ways of saying it. One is start from zeros, you get 128 different numbers. The maximum you can get is 127. Fine. Okay. The other way, of course, is you have to add a 1 to this number. 1 plus 1 will be 0, then 1 carry 1 plus 1 will be 0, and so on. You will get 1 followed by 8 zeros, which of course, 1 followed by 7 zeros, which is of course 2 to the 7. So you add 1 to it, you get 2 to the 7, so the number has to be 2 to the 7 minus 1. What is the smallest number that you can write down in this way?
Minus 127.
Right. That of course is 1 followed by 7 bits. 7 other ones. These bring up the number, that's 127. The one in front tells you it's a negative number, so you get minus 127. So now comes the quiz or the puzzle. How many numbers is that in total? From minus 127 to plus 127?
$255.
255. But how many should we have?
$256.
Good. So how did we lose 1?
Plus minus 0 are being represented as two different numbers.
Right. So you know this, but I'm not very sure whether the others are following, although the others are also asleep perhaps. Anyway, 0 followed by 7 zeros is plus 0, and 0 followed by 7 ones is minus 0. But unfortunately, plus 0 and minus 0 stand for the same thing. So what we have done is we have lost one thing, because we have lost one number simply because of this fact that you have plus 0, minus 0, both represented, two things, the same number represented twice. Now the real question is this. This seems like a rather small problem, right? All you have done is lost one possible number out of 258. In fact, if you were to use 32-bit or 64-bit, the possible numbers would have been 2 to the 32 or 2 to the 64, and you would still lose one out of them. That seems like a very insignificant loss. But we are really very worried about it. Can anybody tell me why? This simple fact that the 0, this is of course the simplest way of representing negative numbers. Just put in a sign in front. End of story. Nobody uses it in computers. It would be a disaster actually to use it. And nobody is too strong. People have tried, but it's really rather bad. So why is this rather bad? The answer is because of this problem of having one less number. But why is that such a big deal? Why is losing one number out of 2 to the 32 or 2 to the 64 such a big deal? Okay, let me give you the answer. The real answer is we are not worried about losing one number, but we are extremely worried about having two zeros or two ways of representing the 0. Why? Because most of the calculations that are in computers, when you take decisions meaning is A bigger than B or is A less than B, which essentially means you are comparing two things with 0 all the time. Is A minus B positive or A minus B negative? Now, if you are comparing with 0 and then all the time, then you have to build in the circuitry to do that comparison in your computer itself directly. It has to be hard-coded in the form of circuits. So two different representations from 0, you have to double your circuitry every time. That is, you would have to compare with the positive 0 and you will also have to compare with the negative 0, which doubles the cost of the circuits, makes them extremely slow because you have to send it to two comparison circuits rather than one. So it's half the speed. So these So the fact that negative numbers are not represented just by putting a minus sign in front is not because people dislike or want to make life more complicated. The way in which negative numbers are represented, the so-called ones complement and twos complement methods, are actually sound very complicated to begin with. But nobody is doing it to make people's lives more complicated. People are doing it so that you can make electronic circuits much faster and more efficient and cheaper. In fact, we could even go so far as to say that if nobody had thought of ways of representing negative numbers in more efficient methods, then the computer revolution simply wouldn't have happened. The computers would have been way too slow and too expensive for people for them to change our lives. As simple as that. So, signed integers, not good. The MSB being +1 stands for negative is fine, but but that is the only thing that you do. You just change the MSB and that makes a positive number a negative number is not a good idea. Next thing that you could do is use what is called a ones complement, which is exactly the output to the XOR, the inverter, controlled inverter that we talked about a while ago. But ones complement is simple. You want to find the ones complement of a number, say this number is negative in the ones complement version is represented by the ones complement of this number, which simply means take all the zeros, change them to ones. All the ones to zeros. And then in the ones complement notation, minus 73 would be represented 10110110. That is, take all the zeros and the original number plus 73, just change each bit, invert each bit. And that, of course, also has the advantage that it changes the significant bit from 0 to 1, indicating that it's a negative number. So you want to find out the negative of this negative number, that get back to 73. That's simple. You just do complement once again. So the 101110 becomes 01001001. You're back. So two ones complement. Doing it twice, that is inverting twice, of course, gets you back where you were. Okay. However, there's still a problem. So what's the largest number now? Largest number, of course, positive number has to start with 0. To be large, it has to have as many ones as possible. Okay. So that's n plus 127. Smallest. The smallest number, if you are writing it in 2's complement, smallest 8-bit number. Come on, what will that be? Simple. You just take the number and invert it. This is going to be the smallest number, right? This number is not minus 0 as it was before for the unsigned integer part. This number is actually minus 127. The plus 1 stands for negative. And because it's negative, we know its actual magnitude is given by inverting this. Yes? Understood? And now, of course, you have another problem, which is you still have 255 numbers. Because you still lost one. And the reason behind this is even here we have two zeros. This is 0, 8 bits. But so is this. Okay, what is negative of this 0? This is plus 0. What's minus 0? Minus 0 is simply obtained from plus 0 by doing a ones complement, which is this is minus 0. So plus 0 and minus 0 are both given by are in fact two of the extreme numbers that you can write down otherwise. And it so happens that plus 0 and minus 0 again has different representations. So one's complement is also bad. Two's complement, on the other hand, solves this. Two's complement does this. You do a one's complement and then add a 1. 1 at the least significant bit. That is 7 zeros and a 1. If you do that, all these problems go away. So I will let you figure out exactly what two's complement does. Okay? And exactly why there is no problem of this doubling of zeros in two's complement. Also, why you get exactly 256 different numbers if you are using two's complement. Same reason. Ultimately, if you figure one out, you will get the other one. So two's complement essentially is one's complement plus a 1 at the least significant bit. Now let's go back and finally complete our rather important circuit here. This is called a two's complement adder subtractor. That's the last circuit I'm going to talk about. This essentially is a nibble adder subtractor because it adds 4 bits. So you have numbers, or it adds 2 4-bit numbers, A3 So how does the addition work? Simple. Addition works simply by standard four full adders, and this addition works when sub is 0. When sub is 0, of course, the carry to the 0th full adder is 0, and the other is just a standard 4-bit full adder. And note that you have XOR gates here, 4 XOR gates. If sub is 0, the input to one input to each of these XOR gates is 0, which means the output is just the other input. That is, remember, it's a controlled inverter. One input is 0, then the other input comes out. So basically, you are feeding A3, B3, A2, B2, and of course A3, B3 and C2 to this full adder, A2, B2 and C1 to this full adder, A1, B1 and C0 to this full adder, A0, B0 and 0 to this full adder when sub is 0. When sub is 1, on the other hand, what you are feeding is entirely different because of this sub being 1. B0, B1, B2, B3 gets complemented. That's the ones complement. But remember, you are now putting in an extra 1 in the 0th carry, which was not there before. That means you're adding an extra 1. That, of course, is the 2's complement of B. You do a 1's complement, add an extra 1. And this actually is a circuit which can add to 4-bit inputs, A and B, A3, A2, A1, A0 with B3, B2, B1, B0, or subtract B from A, depending on whether sub is low or high. If sub is low, it just adds. If sub is high, it effectively changes B to its 2's complement and adds. That's exactly the same as subtraction. So that is exactly how a computer adds or subtracts numbers. This is the circuit that goes on inside. Of course, the full adders are made out of AND or NOT gates, actually AND and NOR gates. And so basically, once you have a full adder, you can put them together to build circuits which will not only add bits but add numbers, and also subtract numbers. So that's all for today. By the way, this part is also very much in the course for tomorrow's exam. Basically, we didn't do much today because we have just used what we learned in the last 2 videos, hopefully, to discuss some very simple circuits. And that's it. So tomorrow at 2 o'clock, we have the exam. Best of luck for that. And then Thursday, we'll have our last class this semester. And then we are going to go on preparing for the final examination. By the way, has the final examination routine come out yet? Yes, is anybody still here?
Yes, sir. I don't think it has come up.
Okay, it has not come out yet. Okay. So there will be a 1 week gap, right, between this, because there will be a lab week, at least, right? After this week, there will be 1 week at least. After that, you will have the written exams, I guess. Okay. The best of luck for tomorrow. Stop the recording and bye for today.